In section 2.3.2, we're going to start to look at what we call limits at infinity. So what this is specifically going to mean is that we're going to be dealing with limits now, where the variable of x is going to be approaching positive or negative infinity. And we haven't really seen this yet in any of the previous sections. Well, let's take a look at kind of what we would mean by this and how our kind of loose and intuitive definition of what a limit means can actually be applied in this scenario. So let's take a look here at the opening motivation. What would we expect the following two limits to actually be? Now you'll notice here that what I have is an arctangent function, arctangent of x. And we should keep in mind that when we have something like y equals the arctangent of x, that's just an alternative way of communicating that we are dealing with the inverse tangent function. Now the inverse tangent function is almost another one of those important graphs to know that can be really, really useful to have on hand. I have down here a nice little set of axes, and we're going to go ahead and actually sketch out what the picture of the inverse tangent function looks like. You might recall that it has a shape that looks something like this. It's kind of like an S sort of a shape, but it levels off over to the right and actually and similarly down to the left. Now in addition to this, there's actually two horizontal asymptotes that occur here on the graph. And these actually occur at the y values of pi over 2 and negative pi over 2. So this is the graph of my inverse tangent function, or my arctangent. So I can start to see here that if I think through these limits, just like we did back in previous sections, answering these questions should be fairly simple. So I can see that if I was to hop on the function of the arctangent and start to follow it as x approaches infinity, I would be curious, what y value do I continually get closer and closer and closer and closer to? So what you can see is that as I move out to the right, my function keeps getting closer and closer and closer to a y value of, well, pi over 2. That's where the function is going. That's why that's a horizontal asymptote. Now, if I was to take a look down here at the next limit, what happens to the arctangent function when I hop on it and I move my x value towards negative infinity? Well, there it should be no surprise that the y values of my graph start to get closer and closer and closer and narrow in on the value of negative pi over 2. Okay, so this is at least kind of the opening idea of what we're working with here. Now, let's take a look down below at kind of this intuitive definition, and we can see that it matches up with the idea that we have here. Suppose we have a function, like the arctangent. It's defined on some interval, starting at some value off to infinity. So there's a graph that exists from some point over. So that way it actually makes sense that there's a path we can follow as we move out towards infinity. Well, then we'll say that the limit of our function as x goes towards infinity will turn into a number, and it'll turn into a number, or what it means to turn into that number is that the values of the function, the y values, can be made arbitrarily close. They keep getting closer and closer and closer to that y value, as long as the x keeps getting bigger and bigger and bigger and bigger. So as we continue to move further to the right, the y value continues to get closer to L. So this is at least the idea here of what our limit as x approaches infinity means. And by just changing around a little bit of the language, you could easily make this have or be a definition when x is approaching negative infinity. So really, really quickly, we can see here that we can begin to apply this to a whole bunch of different graphs and functions. Consider here example number 1. Can I find the limit when 1 over x for the function 1 over x as x approaches infinity and negative infinity? Well, again, if I think about this intuitively based on the picture, I should be able to see that, well, my graph of 1 over x looks like this, and like this, kind of comes in two pieces. And so very clearly, if I follow the graph of 1 over x out towards the right side, and I just keep going and going and going, what I will be approaching is actually this horizontal asymptote, which is y equals 0. That's what I'll be getting closer and closer to, which of course is represented by the x-axis. So looks like I'm running out of space over here, so it's not letting me write. I'll just scrunch that over y equals 0. So I can see here very, very easily that we have the limit of 1 over x as x approaches infinity becomes 0, and as x approaches negative infinity, I can see if I hop on the graph and I start moving towards the left, that means I would have to be on this bottom piece to keep moving left. And it looks like this value is going up, 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 again, towards the value of 0. So both of these limits here end up being 0. Now what's interesting is that we can see that this should be 0 from the picture, but we can also very intuitively kind of gather that from looking at the fraction itself. Work with me in the following way. Suppose that x here was actually a value that was getting larger and larger and larger. Again, x is moving towards infinity. So maybe x is going to be like a billion and then a trillion, right? It's just going to keep getting larger and larger. Well, think about the values of our fraction that we're going to have here. 1 over a billion is a very small number, but as x continues to grow, to say 1 over a trillion, then that fraction gets even smaller as the denominator continues to increase. So when I have 1 over something getting really, really, really big, I know that's going to be something that's becoming very, 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 very small. It's approaching 0. And I have the same exact behavior even when I'm plugging in negative values that are extremely large, because I know that the only difference, and we can see here in the picture, is that I'm just going to have very, very, very small things close to 0 that are negative. So I'll kind of be on the other side of the y equals 0 line. Now, one other thing that we can kind of gather from all of this is the following definition. We can see how this links together with the previous two examples. This definition states that if I ever have a line y equals L, so y equals a number, that would be called a horizontal asymptote of some function or some curve, y equals f of x, under some conditions. Now, we already stated, like in example 1, that this line y equals 0 was going to be a horizontal asymptote. And you may recall talking about horizontal asymptotes in previous classes. What they were there to help communicate was what we called the end behavior of a function. That is, what a graph would begin to approach as you moved out towards the extremes of the graph, either all the way at the right side or all the way at the left. But notice that's exactly the idea that we're communicating here. We're just going to be using these calculus concepts of limits to do that. So notice that we say that a line is a horizontal asymptote of a curve if the limit as I go towards positive infinity is equal to L, or the limit as I go towards negative infinity is equal to L. Notice that in the previous example, both of our limits were equal to 0, and so that was an indication that the line y equals 0 is actually going to be a horizontal asymptote of the graph. And also by that definition, if I was to go back to the inverse tangent function, I could see that the lines y equals pi over 2 and y equals negative pi over 2 should be horizontal asymptotes of the graph, because that's what my limits came out as. So what we have here is a great way now to actually determine horizontal asymptotes of any graph that we want. We would just check the limit as we go towards one side and the limit as we go towards another side. What this means is that ultimately we kind of have three choices for the number of horizontal asymptotes that we might come up with. It's possible, as we see here, that I might end up with two horizontal asymptotes, one as I go in one direction and one as I go in the other. It's possible, like in example 1, I might end up with just one single horizontal asymptote. Or it is possible that maybe we end up with no horizontal asymptotes, and we know plenty of graphs that have no horizontal asymptotes at all. Consider even a simple function like y equals x squared. So horizontal asymptotes and limits as x approaches positive or negative infinity are really tied together in that calculating those limits helps us find those asymptotes.